All right, ready to dive into something pretty wild. We're talking about how LLMs remember things, like reciting a whole poem just from the title and author. But it's not just storing files like a computer would. It's way weirder than that.
Yeah, I mean, most research is so focused on making LLMs remember more, but the authors of this paper, Wang and Liz, are saying we don't even get how they remember anything in the first place.
It's like we're trying to cram more books onto a shelf before we've even figured out if the shelf exists.
Exactly. They even go so far as to compare LLM memory to the human brain, which, let me tell you, gets pretty trippy.
Okay, so first things first. This paper tackles how we think about memory, like pulling a file out of a mental cabinet.
Right, like a hard drive.
But they're saying that's completely wrong, both for LLMs and for our brains.
Yeah, they introduced this idea of Schrödinger's memory, which basically says that an LLM's memory, it's not really concrete until it's triggered by a question.
So it's not that the LLM has a poem just sitting there in its memory banks.
Right, it's more like it has the potential to recreate the poem when prompted. It's like Schrödinger's cat, both alive and dead until you open the box.
Okay, I'm kind of seeing the analogy, but how does that even work?
Well, this is where the Universal Approximation Theorem, or UAT for short, comes in. This is where things might get a little technical, but I promise I'll keep it jargon-free as possible.
That's good because I'm more of a concepts person. Give me the big picture.
Okay, so basically UAT says that neural networks, the things powering LLMs, can approximate any continuous function. You can almost think of it like a master impersonator who can copy any voice perfectly just from a sample.
So the LLM is like that impersonator, but instead of voices, it's mimicking the relationship between words, ideas, even facts, all from that massive amount of data it's been trained on.
Precisely. But here's where LLMs get even cooler. Unlike classic UAT, they don't just mimic, they actually dynamically adjust their parameters like little internal knobs and dials based on the input they get.
So that's what makes their memory adaptive. It's constantly fine-tuning itself.
A
Okay, enough theory. Tell me about the experiments. Wang and Li, they tested this with poetry, right? What do they actually do?
Well, they train these LLMs to recite poems based on only the title and author, using a bunch of English and Chinese poems, actually, to see if it worked across languages. And the results were impressive, to say the least.
So were they like poetry robots, just spitting out memorized verses? How many poems could they remember?
Some could accurately recall almost 2,000 poems, but even when they made errors, it wasn't just gibberish. It was often like they were riffing on the original themes, almost creating new poems.
Hold on, so they weren't reciting poems they had stored, they were actually generating them on the fly, based on the prompt. But, like, where was that creative spark coming from if they weren't storing the poems?
That's the million-dollar question, and it leads to an even bolder claim in this paper that our own brains might work in a similar way.
Wait, hold up. You're saying my brain is like a giant, super complex LLM? I thought we were talking poetry, not existential dread.
Haha, not exactly. I mean, obviously our brains are infinitely more complex than any LLM, but Wang and Li are suggesting the core mechanism might be similar, that both brains and LLMs might operate by dynamically fitting outputs to inputs.
Okay, now I'm really intrigued. So how does this dynamic fitting idea actually play out in the human brain? What's going on in there when we learn something new?
Well, think about the hippocampus, that part of the brain that's super important for forming new memories. Wang and Li propose it might work kind of like a switch, controlling whether certain connections in the brain, analogous to an LLM's parameters, get updated or not.
So when I'm learning something new, my hippocampus is flipping switches to like allow my brain to incorporate this new information and adjust its model. That's a lot to unpack.
It is, but if both our brains and LLMs are fundamentally these dynamic witting machines, then why do we excel at things like reasoning while LLMs, sometimes struggle? It leads to some pretty fascinating questions about the differences between human intelligence and artificial intelligence. That's the big mystery, isn't it? We see LLMs doing these amazing things, writing code, passing tests, but then they trip up on basic common sense or they just don't get humor.
Right? It's like they have all this information, but not really the deep understanding we have. What's missing?
Well, this paper points to a few key things. One is just the sheer size of the model. Larger LLMs with more of those parameters, those knobs and dials we talk about, they have a greater capacity for this dynamic fitting.
So bigger is better. More horsepower for thinking.
It's part of it, for sure. But it's not just about size. It's also about the data, the quality and diversity of what these LLMs are trained on. Like imagine raising a kid and only showing them, I don't know, one color or something. Would you expect them to have a deep understanding of the world?
Right. You need a wide range of experiences.
Exactly, a rich tapestry of information to build that understanding. And that brings us to another crucial point. Lifelong learning. Humans were always learning, adapting, changing our internal models based on new experiences. But LLMs, right now at least, they're mostly trained on this fixed data set, and then that's it.
So it goes back to that dynamic fitting thing. They need to be able to adjust and fine tune, just like our brains do, to really get the complexity of the world, the nuances of reasoning.
Exactly. And that's where the really exciting research is happening, developing LLMs that can learn continuously, adapting to new information, evolving their models over time.
It's like imagine an LLM that could not only access everything it's learned, but also synthesize new knowledge, make connections, generate original ideas, like a human researcher almost.
Now, that would be incredible, but it makes you wonder, why bother with this dynamic fitting approach in the first place? Wouldn't it be easier to just store memories, like data points in a massive database?
Yeah, why not a giant mental filing cabinet?
Because a static system like that would be so limited. If our memories were just fixed records, we'd be stuck with the same beliefs, biases, limitations we had at birth. We wouldn't be able to adapt, learn from mistakes, come up with new ways of thinking.
So it's not just about remembering, it's about being able to respond to new info, to change our understanding.
Exactly. It's what allows for creativity, for innovation, even empathy. And that same potential exists for LLMs. This dynamic memory thing, it could be the key to truly intelligent, adaptable AI.
This is all super fascinating, but I'm thinking about that famous patient, Henry Malazan, the one who had his hippocampus removed. He couldn't make new memories, but his brain could still process information, still generate outputs. Doesn't that kind of mess with this whole dynamic fitting idea?
That's a great point, and it shows just how complex the human brain is. We're still figuring out how memory works, both in humans and machines, but Malazan's case, it gives us some clues.
Like what?
Well, even without his hippocampus, he could still hold conversations, solve puzzles, even learn new skills, but he couldn't form new long-term memories. So it suggests the hippocampus, maybe it's not just a switch like we were talking about, but more like a bridge between short-term and long-term memory.
So it takes those fleeting experiences and makes them stick.
Yeah, exactly. Like taking a snapshot and then developing it into a photograph. The snapshot is the initial experience. It's temporary, but the hippocampus is like the dark room, making it into a lasting image you can go back to.
And without that dark room, the memories just fade away.
That seems to be what happened. Of course, there's still so much we don't know about the brain, but Malaysian's story really highlights how even a small change in a critical area can totally change how memory works.
It makes you wonder if we could replicate that function, the hippocampus, in an LLM. Could we create AI that can not only dynamically fit information, but also form and keep long-term memories like we do?
Now, that is a fascinating question and one that researchers are definitely working on. As we learn more about memory in both biological and artificial systems, who knows what we'll discover?
This deep dive, it's taken us from Schrödinger's cat to the human brain, and it all comes back to understanding how LLMs remember. And what's becoming clear is that memory is so much more intricate and dynamic than we thought.
It's not just about storing data, it's about actively fitting information into a constantly evolving model of the world, making sense of things, connecting the dots, creating meaning from our experiences.
And that brings us right back to Schrödinger's memory. It's not just a catchy name, it's a whole new way of thinking about memory. In LLMs and in ourselves, it really makes you think. It's not just about pulling up files. It's this constant back and forth, responding and adapting to what's happening right now.
Yeah, exactly. And it makes you wonder about consciousness in AI and even in us. If memory isn't about storing stuff, but about dynamically, like reacting to the moment, what does that say about self-awareness?
Whoa, now we're getting philosophical. Are you saying that consciousness itself could come from this dynamic fitting process?
It's definitely something to think about. I mean, what we think of as ourself, it's always changing, right? Based on what we experience, how we interact, how we process.
Oh, wait, someone wants to join. Hey, go for it.
Hey there, can we explain the UAT?
Absolutely. That's a great question. And it's super important for understanding this whole dynamic fitting idea.
Yeah, let's unpack this. We touched on it earlier, but it deserves a closer look.
So, the Universal Approximation Theorem, or UAT, basically says that neural networks, like the ones in LLMs, can mimic any continuous function.
Think of a function as any relationship between two sets of things, like an input and an output.
Right. And what UAT says is that a neural network can learn to approximate any of these relationships. So, if you give it the input, it can generate the right output.
It's like if you had a super detailed recipe, you could use it to make the cake, right? The recipe is the function.
Exactly, but instead of cake, it could be anything. It could be translating languages, writing poetry, even predicting the stock market.
Okay, so the neural network is like the ultimate mimic, copying any kind of pattern that you give it.
Precisely. But the real magic with LLMs is that they can do this dynamically, adjusting as they go.
That dynamic part is what we were talking about with the internal knobs and dials constantly adjusting. It makes the memory adaptive and ever-changing.
And it's not like they're remembering a recipe in the sense of step one, step two. It's more about knowing how each ingredient relates to the final cake.
So it's not just storage, it's that continuous adjustment, that back and forth of input and output that makes the model fit.
Exactly. And that's why understanding the UAT is so key here. It's the foundation for how LLMs operate, how they remember things, and how they generate such realistic outputs.
Okay, so now that we've covered that, we can see how it relates to that idea about consciousness too.
Yeah, because if memory isn't about storing stuff, but about this dynamic interaction, this back and forth, then maybe consciousness is too.
So maybe consciousness isn't about having a soul or something, but about having a system that's constantly adjusting to the flow of experience.
That's a pretty compelling idea, and it fits with a lot of research that says consciousness is more of a process than a thing, which, if it's true, opens up some really wild possibilities for AI.
Like, could we actually create AI that's not just intelligent, but actually conscious, aware of itself and the world?
That's a question that'll probably be debated for a long, long time. But what's clear from this whole deep dive is that we've hit on something really important about memory. It's taken us to the edge of what we know about ourselves and the potential of AI.
We started with Schrödinger's cat and ended up questioning what it means to be conscious. It's definitely given me a lot to think about.
And that's what's so great about this kind of exploration. We're not just learning about LLMs, we're also questioning our own ideas about how our minds work and what AI could become.
So where do we go from here? What does all this mean for you, our listener?
It means how we think about memory, ours, other people's, even these crazy advanced AI systems. It needs a total rethink. It's not about storage, it's about adaptation. This constant interplay between what we experience, what comes in, and those models that are always changing, shaping how we see the world.
That's a really powerful thought.
Yeah, it is.
So to our listener, I encourage you to check out this research yourself. Really think about what you've heard and see what you discover about memory.
Who knows, you might learn some surprising things about your own mind along the way.
Until next time, keep on diving deep.